Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, and welcome to Week 2, Lecture 3 of Dynamic Atomic Force Microscopy Methods. In the last class, we had actually introduced the two important modes of imaging and force spectroscopy, which are respectively the amplitude modulation AFM mode, or tapping mode, commonly known as tapping mode, or the frequency modulated AFM mode. These are two important modes that we tried to explain the physics of image formation and what are the channels of material contrast that appear in these channels when one scans over a sample. We did everything on the basis of linearized theory. In other words, we talked about basically representing the tip-sample interaction forces by a linearized version, by a straight line slope and a simple viscous dashpot representing the tip-sample interaction forces. So today we're going to try and expand that definition a little more, and we're going to talk a little bit about how to start thinking about both tapping mode and frequency modulation AFM without requiring this constraint of linearizing the equations to understand the physics of image formation and the material contrast channels. In particular, in this slide, I'd like to focus a little bit on what are the limitations of the linearized analysis that we performed last time. The point mass model for what we're trying to understand is shown on the top left. You got an externally driven oscillator, and there are tip-sample interaction forces, FTS. Z and Q and D. D is the instantaneous gap between the tip and the sample. Q is the displacement of the tip as it oscillates up and down. And Z is the position of the tip with respect to the sample when there are no tip-sample interaction forces present. Now, what I've shown on the right is a typical conservative interaction curve for tip-sample interaction forces, FTS cons, as a function of D, which is the distance between the lowermost atoms on the tip and the uppermost atoms on the surface. And it has this typical canonical attractive gradient and then a repulsive gradient as you come very close to the sample. Now, what we talked about last time was that when you bring an excited cantilever very close to the sample, there's going to be a bit of a sag of the cantilever. The cantilever is going to bend a little from its undeflected equilibrium by an amount Q star, and then about that Q star there's going to be Q tilde oscillations due to the excitation, due to the interaction forces. And what we had said is that in order to understand dynamic AFM, both FM and AM, one needs to start making the assumption that the local interaction forces, FTS, conservative, can be written simply as KTS times the displacement Q tilde, where KTS is the force gradient, which is defined in a manner such that a repulsive force gradient is positive and an attractive force gradient is negative. That's K sub TS. So this is simply the slope of the force versus distance graph with a negative sign to ensure that a repulsive gradient gives you a positive value for K sub TS. In a similar manner, we had to assume that the dissipation forces can be written out as a negative CTS, a viscous dashpot, times Q tilde. What you see on the graph on the right is trying to give you a sense of when do we think that this approximation is valid. And you see this interaction force, and you see the equilibrium position, D star, that the tip is sort of hanging at the distance D star under the equilibrium of tip-sample interaction forces and the restoring forces, and then you've got this Q tilde oscillation happening about it. The width of that oscillation is about 2A, A towards the sample, A away from the sample from the equilibrium distance D star. So that's the band in which one is oscillating. Well, in order for this approximation to be valid, it's very clear that the oscillation amplitude needs to be small enough such that the interaction force can be represented by a straight line. And if you ask yourself the question, under what conditions could you write or could you describe the interaction force in that band of oscillation in which the tip oscillates, in that region in which the tip oscillates? Can it be described by a straight line with a fixed slope or not? And the answer to the question is simply, if one goes back to some Taylor series analysis, the answer is the amplitude of oscillation needs to be much smaller than d star, which is the tip sample gap. When one does high-resolution atomic force microscopy, basically the d star, the small, you're trying to operate with very small oscillation amplitudes, especially when you do high-resolution AFM. And let us say d star is 1, which represents roughly 1 to 2 nanometers, is roughly the gaps at which Van der Waals forces become active between the tip and the sample. So if you're talking about d star being roughly of the order of 1, and the tip located so close to the sample that it's sort of hovering at about a 1 to 2 nanometer distance from the sample as it oscillates, in that case, the oscillation amplitude needs to be much smaller than d star for this approximation to apply. So it needs to be less than even a tenth of the tip sample interaction force, which needs to be less than an angstrom typically. So the conditions under which you can describe everything from the scanning to the physics of image formation in these two modes to understanding contrast channels would then require you to use oscillation amplitudes to be extremely small, typically less than an angstrom, for you to be able to use this theory, the simple linearized theory, to explain and interpret one's answers. Naturally, this doesn't usually happen in practice. Under most application conditions, most people are going to be using oscillation amplitudes anywhere between 2 or 3 nanometers to upwards to about 50. And the conditions under which you might actually be able to assume linearized analysis very rarely hold. There are some special cases where they might hold, but in the majority of cases, majority of conditions, these would not be valid. So what happens then if the oscillation amplitude, the band in which the tip oscillates, is a little larger and occupies a little more of the tip sample interaction force curve? I've tried to demonstrate that in these 3 graphs that are shown here. On the left column, we've got the situation where we can regard the oscillation amplitude as the tip oscillates left and right, that it's the region it traverses during the oscillation is so small that you can regard the tip sample interaction forces as a straight line with a constant slope. In which case, if you're able to do that, and if you sweep the frequency from below resonance to above resonance, the excitation frequency, the amplitude and phase lag response will be as shown here. There's a nice peak, it goes down, and the phase has this nice canonical behavior starting from 0 to plus 180 degrees of phase lag when you go above resonance. But this requires, remember, as we tune the frequency, from low to high frequency, the maximum amplitude, even when it's really at the peak oscillation amplitude, needs to be much smaller than d star, which means at the maximum peak amplitude needs to be about less than an angstrom for us to be able to think of resonance peaks, nice canonical resonance peaks like this. However, what ends up happening is when you go to slightly larger amplitudes, as shown in the second column here, where the tip now clearly, as it oscillates in this range of oscillation, the interaction force it encounters can clearly not be represented by a straight line. But there is a definite big curve in it, and the tip oscillation takes it all the way to the bottom of this tip sample interaction curve, and we would call this what we call the attractive regime. It stays within and encounters attractive forces. In this case, it turns out that if you were to sweep the excitation frequency from below resonance to above resonance, this is a clearly nonlinear setting now, because the oscillation amplitudes are not much smaller compared to d star. It turns out the resonance curve would change in the following manner. Instead of being this nice canonical form, it actually bends at the very top towards lower frequency. Now, these are very interesting nonlinear effects that are described very well in some of the literature mentioned at the end of this of this lecture notes in the appendix. And what also happens is the phase curve also starts distorting as I show you. If one, on the other hand, does a tuning curve where at peak, when it's really at resonance and oscillating pretty hard, if the tip actually oscillates back and forth and covers a pretty large range of tip-sample interaction forces, both from the attractive all the way to the repulsive, so the amplitude is comparable to D star. In this case, the resonance response is no longer the simple canonical result. Peak, it actually bends and turns around, and the phase also distorts significantly. The key point is that this simple understanding that we talked about last time really breaks down as soon as the excitation, or as soon as the oscillation amplitudes cannot be regarded or can be regarded as finite relative to D star, or the gaps at which you're operating. This creates many interesting challenges in dynamic AFM, both for tapping mode as well as for frequency modulated AFM, in that we now have the possibility of multiple oscillation states. So you can imagine when these resonance curves bend around at a given drive frequency, you can actually have multiple oscillation states that can occur. And this leads to some very important global instability issues, both in tapping mode AFM and in frequency modulated AFM that we'll talk about later in the class. But this is just, without showing you how this actually happens at the moment, this is just to give you a qualitative description of what happens when the oscillation amplitudes are larger than, let's say, an angstrom. These are the kind of situations that arise, and we have to, therefore, in all realistic or most realistic conditions of AFM, we need to deal with these, resonance curves that turn around. So any theory that we use to try and interpret and understand the physics of image formation and material contrast in AFM needs to acknowledge these kind of effects. So what we'll do in today's lecture is try to focus on two important concepts that relate to the analytical theory of AFM, where we'll describe today two important quantities that relate observables in dynamic atomic force microscopy, which are typically the amplitude, phase, frequency shift, or phase shift, or excitation amplitude, to quantities that are related to tip-sample interaction forces. These are going to be called, respectively, the dissipation and the virial. So let's begin with this and write down the equations of motion for the directly excited point mass oscillator model interacting with the sample. I have gone ahead and written the tip-sample interaction force as the additive decomposition of conservative interactions and dissipative interactions. Remember, the conservative interactions are those that depend only on the gap, D, and therefore they can be regarded, the conservative interaction forces are associated with the tip-sample interaction potential energy as well. And the dissipative interaction forces are change the direction depending on whether you're approaching the sample or moving away from the sample. So the equation of motion we're going to deal with is equation 1. And fundamental to the analytical theory of dynamic AFM is that when you drive this oscillator at near resonance away from the sample and come close to it, that under the interaction or the perturbations from the tip-sample interaction forces, we continue to assume that the tip keeps oscillating in a nice harmonic fashion, in a sinusoidal fashion, without having too many anharmonics or any major distortions. This is a basic assumption that's key to the perturbation theory, which forms the foundation of dynamic atomic force microscopy. And the appendix lists certain cases where one needs to worry about effects that or conditions under which these perturbation approaches don't hold. So what we do here is we assume a steady state solution, Q, the tip displacement equals A sine omega t minus phi, and the velocity Q dot then is going to be A omega cosine omega t minus phi. We're, for the moment, neglecting Q star, which is the steady deflection of the tip under the interaction forces, mostly because this tends to be much smaller compared to the oscillation amplitudes. And we're going to define a new variable theta, which describes the progression of time. You can think of theta as being a rescaled time because when theta goes from 0 to 2 pi, what's basically happening is you're completing one cycle of oscillation. And in terms of theta, then the tip motion is going to be given as a sine theta, and q dot, the velocity, is going to be given as a omega cosine theta, equation 2. So the next slide then tries to describe what we're going to do with the perturbation approach, or using the approximate theory to understand these links between observables and the dissipation in Virial. So what I've plotted out here is I've got a sample surface shown in gold, and the tip is located at an undeflected position Z above the sample surface. Above the sample surface, I've got a little shaded area which represents the fact that above the sample surface there's a small range of distances for which attractive forces are being felt. So even though the surface begins at Z equal to 0, a little above it, one actually encounters some interaction forces as well, attractive interaction forces. So Z represents the distance between the undeflected position of the cantilever tip and the sample surface, and the red curve represents the motion of the tip as it undergoes a sinusoidal oscillation of the type that's been assumed in the theory. So Q is going to be equal to a sine theta, and so the tip goes up in time, comes down to the bottom, and moves back up. Theta cycles from 0 to 2 pi. Theta cycling from 0 to 2 pi is basically one oscillation cycle under the excitation force. Now, what's going to happen is, as this happens, D, which is the instantaneous tip sample gap, is going to be given by Z plus a sine theta, which means that there's going to be a maximum D, D max, which is going to be the furthest distance of the tip from the sample surface during the oscillation cycle, which is going to be Z plus A. In a similar way, there's going to be a Z minus A, which is going to be the closest approach distance of the tip from the sample. The most important thing to notice here is that the point where the tip begins to interact with the sample is not in the first half of the sine curve, but it actually is in the second half of the sine curve, because the very bottom of the sine curve, it reaches a value of sine theta reaches -1 at 3 pi over 2, which is where the tip goes to the very bottom position. And so if you look at the intersection of the red curve with the sample surface as well as the region where you have attractive interaction forces, the intersection tells you what ranges of theta values, between which range of theta values do you get interaction. And those are shown or depicted in this graph as what I call interaction time. So the interaction time is this band of theta in which the tip is feeling the interaction forces. For the rest of the oscillation cycle, the tip does not feel the interaction forces. Speaking of the interaction forces, let's move to the sketch below. Below, I have plotted a combination of tip sample interaction forces, both the conservative part and the dissipative part. The dissipative part is plotted in green, the conservative force is plotted in blue. Let's take a look at the blue, the conservative interaction force. First of all, starting from theta equal to 0, the tip is far from a sample, so it does not feel any interaction forces, so the blue is basically 0. Until the tip moves forward and enters this regime of attractive interaction forces, in which case the blue starts dipping down because of attractive forces. As the tip goes further down towards 3 pi over 2, the conservative interaction force turns around and becomes positive, increasing until you reach maximum indentation at 3 pi over 2. And then as the tip turns away and comes back out, the conservative interaction force literally repeats itself from before with a mirror symmetry, because the conservative interaction forces just depend on the tip sample gap D, not whether you're approaching or retracting from the sample. So when you move away from the sample, you get a mirror image of this, because it's going to be perfectly symmetric with respect to the 3 pi over 2 position. On the other hand, when you look at the dissipative interaction forces, they change their value depending on whether you're approaching the sample or moving away from the sample. So when one approaches the sample, the green, which is the dissipative interaction force, starts increasing, it reaches the maximum indentation, at which point it turns around. As soon as it turns around, the direction of the dissipative force changes, and it becomes skew symmetric with respect to 3 pi over 2. The important thing is both the dissipative and the conservative interaction forces exist and act on the tip only during this interaction time. So with this setting, let's go ahead and describe the theory behind how we deal with the definition of dissipation and virial. So we take equation 2, which is a sine theta and a omega cosine theta, plug it into equation 1, and we get this expression. And at this point, we're going to define two important quantities that I mentioned already. V sub ts, which is going to be what we call the virial, and the second quantity is E sub ts, which we call the energy dissipation. The first term is the virial, and it represents, the pointy brackets represent average value. So whenever we use pointy brackets, it refers to average value of the quantity inside it. So it refers to the average value of the conservative interaction force times the tip displacement coordinate q over an oscillation cycle. And I've written it out in terms of an integral now, where we have 1 divided by the time period, integral from 0 to time period of the tip sample interaction force multiplied by q, its position, times dt, where dt is the small interval of time. It can also be written in terms of d theta, as shown on the right. We'll come to the physical significance of V sub ts. For the moment, we just define this quantity as the average value of the product of conservative tip sample interaction force times the tip displacement over an oscillation cycle. The second quantity is the negative of the dissipative interaction forces times q dot dt. So this literally is trying to measure the work done due to dissipative tip sample interaction forces. And again, the physical significance of it will be dealt with later. The important thing is that this ETS quantity is not an average quantity, so it's not divided by the time period. It is the overall energy over the tip sample cycle. So once we define these two quantities, we can go to the equation shown on the top of the slide and multiply through by a sine theta and divide by 2 pi, and we get a very nice expression for the virial V sub ts, which is shown in equation, at the lower equation. If we take the same equation and multiply it by a omega cosine theta, integrate from 0 to 2 pi, we get a simple expression for E sub ts, which is the energy dissipation. In terms of quantities which we could regard as the virials, as the observables in AFM, which are natural frequency, drive frequency, or excitation frequency, Q factor, amplitudes, and so on. The important thing is that both virial and energy dissipation have the units of energy, which means they're usually written out in terms of electron volts or attojoules or nanojoules, and so on. So let's go over the physical meaning of E sub ts. As shown at the very top, E sub ts depends on z, which is the distance you're going to be from the sample, and depends on the oscillation amplitude. If you're at a large z, which is small oscillation amplitude, you don't experience any tip sample interaction forces, and energy dissipated is going to be 0. On the other hand, as z decreases, energy dissipation tends to go up. As amplitude increases, energy dissipation tends to go up. So ETS is a quantity that will depend both on z and on amplitude. And I've described this on the very top in terms of the time integral, but also written it out in terms of an integral in terms of dq, which makes its interpretation very simple. What I've shown at the very bottom is typical tip sample interaction force with hysteresis involved. So as a function of d, when you approach the sample, the interaction force increases. When you move away from the sample, it follows a different direction, which we can break up into a conservative part, the additive sum of a conservative part, and a purely dissipative part as shown. The integral on the very top, as shown, is actually going to be 2 times the integral from minus a to plus a, which means that it basically represents the dissipative interaction force times dq moving forward plus moving backwards, which basically means it is the area under the forward direction and backward direction force versus D curves shown in the bottom right. As a result, what you're basically measuring in the E sub TS is the energy lost to the sample during one cycle of oscillation. It is irreversible work done by the tip on the sample, and the reason why it's by the tip on the sample is there's a negative sign in the integral description. If the negative sign were not that, it would represent the work done by the tip-sample interaction forces on the cantilever. By putting a negative, we're trying to reverse it and saying this is the work done by the cantilever tip on the sample. So this is the energy dissipated in the sample. Where does the energy get dissipated in? In a number of effects, and we're going to talk about this later, but it could go into phonons, into increasing the temperature, it could go into anelastic effects, it could go into many irreversible processes, relaxation, if you're talking about polymers, many dissipation processes that have to do with rearrangement, molecular rearrangement on the surface, irreversible arrangement due to tip-sample interactions. If you look at the physical meaning of VTS, which is virial. This is a quantity which is a little harder to understand than the energy dissipation. And in the appendix, I've derived an expression for the virial in terms of dq as opposed to dt or d theta, in terms of dq, which is increment, and q, the tip displacement, and that's shown out here. Now, I'm going to go to the board now and try to describe the physical meaning of this virial. So the expression for the virial is shown up here. It again is a function of z and a. If z is very large and you're oscillating and you don't feel any interaction forces, VTS is going to be 0. So as you come closer to the sample, z decreases, VTS becomes non-zero. In a similar manner, VTS depends on A. If A is very small, then it's not encountering the tip sample forces. If A is very small and you experience only the attractive forces, you'll get certain values of VTS. If A is large and you're experiencing repulsive forces, you get a different value of VTS. So it depends both on Z and on the oscillation amplitude. This is the expression that's been derived in the appendix. What's important here is that it consists of two different quantities. The first is K sub Ts, which is the tip sample interaction force gradient, times dq. And one would understand that in the context of this graph here. So what I've graphed here is a canonical gradient, tip sample interaction gradient versus d graph. This is not f versus d, this is rather K sub Ts versus d, which is the gradient. And there's remember, we have put a negative sign here to ensure that the gradient is positive and it's repulsive. Now, let us say that the cantilever is located at a position z from the sample. And let us say that it's actually going to be oscillating like so, with an amplitude A. In that case, if you look at this quantity KTS times dq, integrated from negative A to plus A, it basically is looking at the area of the KTS graph as a function of D, this area, shaded area out here. However, we also have this additional term out here, which is a weighting function. So the integrand here is actually not the area, it's not just the area under the KTS versus D graph during the oscillation cycle, but it's weighted. And this quantity is a weight that reaches a maximum value of 1, and it extends over the plus A to minus A range. So this represents a weighting function that does this. Reaching a maximum value of 1. So really what this integrand represents is a weighted area under the KTS versus D graph traversed during the oscillation cycle. The product of these two is what we're integrating, and that's the integrand that we're dealing with. So in the limit that, so with this expression, we can go back to the formula shown in the slide. And if you take a look at the limiting case when the oscillation amplitude is very, very small, i.e. we're dealing with linearized analysis, you can show, as I've shown in the appendix, that the virial, which is a function of z comma a, can be very easily described as the tip sample interaction gradient at z, kts, times a squared divided by 2. This is in the limit of very small oscillation amplitudes, which means that in this limit, we can regard the tip sample interaction virial as being the maximum potential energy stored in the conservative tip sample interaction forces due to the oscillating, as encountered by the oscillating tip. But when the oscillation amplitudes are larger and the linearized theory doesn't apply anymore, then we have to regard it as the weighted potential energy stored in the tip sample interaction due to the tip sample interaction forces. VTS is also sometimes called the virial, and I've talked in the appendix about why it's called the virial, because it can be derived using the virial theorem as well. And so what we have done, therefore, is talk about these two important quantities, ETS and VTS, which are going to be two quantities that are related to the tip sample interaction forces. And yet, it's important to remember that we measure these two quantities both in frequency modulated AFM and in amplitude modulated AFM through the observables, which are amplitude and phase of oscillation. Thanks.